Good morning, class. I'd like to welcome you to this week's lecture on sampling concepts. So before we get started, let's talk about what we did in the last class. We discussed the importance of analog signal conditioning, specifically focusing on filters to shape our signals. We also talked about the best practices for grounds, shielding, connecting wires, to minimize noise in our measurements. And this lecture is going to build on those concepts, as proper signal conditioning is essential for effective sampling. Now today's lecture is going to be pretty straightforward. We're going to focus our attention on sampling concepts. Now my goal for today's lecture is to do a couple of things. First, we should be able to clearly differentiate between analog time, discrete time, and digital signals. And I think probably more importantly for practical work, you'll learn how to select the correct sampling rate to prevent a real problematic issue, which we call aliasing. Now in the real world, when we measure something, we get this analog signal. It's a continuous signal from a sensor. And we need to convert that into a discrete time signal that a computer can understand. Understanding, I think we talked about last week, it needs to be a 1 or a 0. You need an actual point. You can't have a continuously variable signal. And this process is called sampling. And the quality of this discrete information depends on three things. The original signal's frequency content, and secondly, the time between each sample, which we call delta t, and the total duration of our measurement. So in this case, we're looking at 10 discrete measurements along this analog signal, so n is equal to 10. And there's also a time increment, delta t, which is the inverse of our sampling rate. So that's just something to remember. Okay, now this is the most important concept of today's lecture. And the sampling theorem provides a rule that we need to follow, and it states that to properly capture all the frequency information in an analog signal, our sampling rate, which is fs, must be more than double the maximum frequency present in the signal, and that's fm. If we express this in terms of the time increment, which is delta t, the formula delta t must be less than 1 over 2 times the signal frequency. And the images on this slide, if you look at the first two images, this is the initial sample rate, this is the initial analog frequency, and then following the rule we get this really nice representation of what the signal that we've created in digital time looks like. And then these next two images here is what a signal looks like created not following these rules. And you can see that this really doesn't look like the original signal here in A. Now, when we violate the sampling theorem and sample at a rate less than 2 times the frequency, that's when we get into some trouble. This leads to aliasing, where a higher frequency is misrepresented as a lower frequency in our new digital data. And this really is a fundamental problem, because you can't tell the true frequency from the aliasing frequency. And the Nyquist frequency is defined as half the sampling rate. And this is really a critical value, and it represents a point for where values will fold over and create this aliasing phenomenon. So here is a folding diagram, and what this really helps explain is a value of a signal that has a frequency above the Nyquist frequency will fold over and appear in your sample data as a false frequency. And really that's what you see here. If you look at this value of almost 1.7, it folds over and in your data looks like a value of just over 0.3. Okay, so we've just identified that aliasing is bad. You have an analog frequency, you are sampling it, and if you sample it at too low of a period, you end up getting this false frequency that is misleading. And so how do we prevent this aliasing? And there's really two different strategies here. The most effective method is to use a low-pass filter. We also call it an anti-aliasing filter. And this is before you even get started sampling. This filter is set to the Nyquist frequency to remove any high-frequency components that could cause aliasing. And I guess the second option, it's a bit less effective, is to just use a higher sampling rate. You just keep sampling and sampling faster and faster and faster until you get good data that stops changing. And I know it's a less effective, we talk about being less effective, but it's what a lot of people do. This can minimize the problem, but it doesn't guarantee a clean signal and can create huge data sets. So you might end up with thousands of data points that you really don't need if you just did the homework and threw a low-pass filter in there. And I think a good rule of thumb for most applications is to choose a sampling rate that is at least 5 to 10 times the maximum frequency you care about. So figure out what the frequency is, sample at 10 times that, throw in a low-pass filter at the Nyquist frequency, and then usually you're good to go. Okay, so the process, the methodology that you use is you first increase the sampling rate, and then you kind of look at the signal and see how it is changing, and there'll be a point where it kind of stops changing. You say, hey, I think this looks good. Then you'll compute the amplitude spectrum for the signal, and then you're really looking at how do these change and with the different frequencies. And then you throw in an anti-aliasing analog filter at the Nyquist frequency. So you use the data that you've collected to work out the Nyquist frequency, and then you throw in an analog filter. So that's kind of the process, the steps that you take to sort this out. So now let's talk about a related issue, amplitude ambiguity. This refers to how accurately our sample data represents the original signal's amplitude. A discrete Fourier transform, DFT for short, is a mathematical tool that we use to find the frequency content of a discrete signal. And the DFT is most accurate when our total sample period, it's that n delta t number, is an exact integer multiple of the original waveform's fundamental period, t1. And when this is true, the amplitude of our DFT is accurate, and we can perfectly reconstruct the original signal. And of course, if we say that integer periods are the best, okay, what happens when we're using non-integer periods? And I think you can see here in these graphs, you don't get it's not coincident with the period, and so the DFT doesn't like exactly represent the sample continuous waveform. So this is called amplitude ambiguity, and we really try to avoid this, and it's just something we don't fool with. So if we go ahead and our total sample period is not an integer multiple of the original signals period. We really don't want to do this, but when it happens, we run into a problem called leakage. So instead of seeing a single sharp peak at the true frequency, the energy kind of leaks out into the surrounding frequencies, creating a broader noise spike. And this makes it difficult to determine the exact amplitude of the original signal's frequency component. And the DFT resolution, that delta F, can be adjusted to minimize this effect, but it's really just important to understand why it happens in the first place. So just to summarize what we've learned, the quality of our digital signal representation depends on two key factors: the sampling rate and the DFT resolution. And so we use the sampling theorem to ensure we're capturing all the necessary frequency information and avoid aliasing. And we can then manipulate the DFT resolution to ensure the amplitudes of those frequencies are accurately represented and to minimize leakage. So by mastering these two concepts, I think you'll be in good shape to acquire and analyze data correctly in your projects in the future.